Okay, so we are to the final lesson in this half of Unit 3. I split Unit 3 into two separate units because I feel like there's different content and I wanted to separate that. So what we're going to work on today is solving linear systems in three variables. So here I have the steps to solving these, and these systems have variables x, y, and z. So what you want to do is you want to make sure that your system has each equation with x, y, and z all on the same side of the equation. All on the same side. So all on the left-hand side, I would say. You choose a variable to eliminate, and then you choose only two of the three equations to eliminate that variable. And I'll talk about that. Select a different variable or different set of two equations and eliminate the same variable. So if you chose to eliminate x with two equations, choose two different equations and eliminate x from those. Then you have a two-variable system, and then you can solve that system using elimination. So I'm going to jump right into that because the last three steps there are mostly repeating. So if I look at this system, what immediately catches my eye is that in the equations 2 and 3, think of this as 1, 2, and 3. In equations 2 and 3, the x's match up actually. So for this one, I'm not going to rewrite it. What I'm going to do is I'm going to show adding these equations together right here. So x automatically eliminates there. I get 8y plus 10z equals 74. So I decided to eliminate x. So what I am going to do is I'm going to take equations 1 and 2. So the first equation, and then the second equation, I'm going to think about what do I have to multiply by that second equation to get the x's to match up. I'm going to multiply the second equation by 3. So the second equation becomes negative 3x plus 15y plus 36z equals 73 times 3, which is 219. And then I add those together, and I should see that 3x and negative 3x cancel. So this becomes 13y plus 40z equals 239. So you see how I have a two variable system there. So I can line things up in that two variable system. I'm going to do that in a different color, maybe. So I'll have 8y plus 10z equals 74, and then 13y plus 40z equals 239. So I'm lining those up. Then I'm going to just solve that system like we'd been solving systems before. It's going to be easier to get z's to match up. So I'm going to multiply the top by negative 4 to get 10z and 40z to match up. So the system becomes negative 32y minus 40z equals 74 times 4, negative 296. And then you got 13y plus 40z equals 239. So when I add those together, the z's cancel. And then negative 32 plus 13. It's going to be negative 19y. And then negative 296 plus 239 is going to be negative 57. Divide both sides by negative 19. I get y is 3. So that's a lot of work just to get y. But now it becomes easier because I can find z by plugging into one of these two blue equations here, one of these two variable equations. So I'm going to plug it into the top one, 8y plus 10z. So that would be plugging in for y is 3. It would be 24 plus 10 z equals 74. So then 10z equals 50, z equals 5. So there's two of them. Now we still got to find x. So I'm going to go all the way back into one of my very original equations. I'd plug into equations 1 or 2 or 3, I guess. So let's plug into equation 3. This would be x plus 9 minus 10, since y is 3, z is 2. And that equals 1. So x minus 1 equals 1. And then x equals 2. So my last way I'd show this solution, okay? The last way I'd show this solution is as a 3-point or a 3-value point, ordered triple, you'd call it. 2, 3, 5, okay? And that was one example that took me about 6 minutes to explain, okay? So this is tough at first. So first thing, think about eliminating one variable from two different equations or two different systems that you set up. You're working to get a two-variable system. You know how to solve two-variable systems from the last few lessons.